Okay, in this tutorial, we're going to have a little look at logarithmic graphing, which is a technique used to graph data where there are extreme differences in the values of that data. Now, I'll go have a little talk through the main resource on this web page. But before I look at this, I'm just going to introduce the idea of logarithmic graphing by looking at this graph here. So this graph shows you the number of internet hosts on the World Wide Web in 1981 through to the year 2012. And what we can see that back in 1981, there was a couple of hundred internet hosts in total on the whole planet. And that's to be expected because it was literally a new invention at that particular point in time. Whereas if we go to the year 2012, we can see from the number over here that we have 1,000 million. So we have 1 billion internet hosts or internet web pages on the World Wide Web back in 2012. Now, the most obvious problem here is how do you plot on a graph on a vertical scale 200 and 1 billion? Because there's a significant jump. On the horizontal scale, well, that's a regular one. You're just looking at every 4 years what's been the change. Okay, but the problem is on the vertical scale, which is the number, you've had this significant jump in the number of web pages. So what you do is you use a logarithmic scale for your y-axis. And what that means is that the first jump is from 100 to 1,000. So each small little interval up here would be 100 going up to 1,000. But then each tenth between here and the next scale is going up in thousands, whereas only hundreds between here and here. Now we go up 2,000, 3,000, 4,000, 5,000, all the way up to 10,000. Between here and here, we're no longer going up in thousands, we're going up in 10,000s. So from this point to this point, it's in 10,000. So when we get up here, we're at 90,000. Once we reach this point, we start going up in intervals of 100,000. Till we get to here, then it's 1 million, 10 million, 100 million, and 1 billion. And if we had one higher, then it would be 10 billion. What that allows us to do is see that where the big jumps are. And it allows us to plot that change across time, allowing to show both very small values, like down here, and very big values, like we have up here. And we are able to do that on one piece of graph paper. If we didn't use a logarithmic scale for our y-axis, this line would go extremely high. It would be impossible to graph that and be able to make it visible. Now, if we have a little look at the actual example, how it's used in geography, one of the problems when you're looking at the power of rivers to move material and how much velocity you need in a river to actually move the stuff that's in the river, you have to deal with the Hjolstrom curve, as it's known. And because the size of particles actually ranges, so the smallest stuff floating in a river would be a clay particle. And a clay particle is 0.001 millimeter, so it's minuscule. Now, in that river, you may also get sizes of stones that are 10 millimeters, so like a centimeter, or even 10 centimeters, like we have up here. So these are much larger. These are stones. We might have particles of sand, which could be between 0.1 millimeter up to a centimeter. Likewise, we have silt at 0.01. Now, trying to plot the size of particles in a river on one horizontal scale becomes impossible because of the difference in the clay particles and the stone, just because they're so different in size. And you can see we're using the logarithmic jumps that we had before. So between here and here, we're going up in thousandths, then in hundredths, then in tenths, and then we're going up in ones as units, and then we're going up in tens and so on. And the same actually happens on the y-axis, because the velocity of the river can vary greatly from almost nothing to a very fast-moving river at over 1,000 centimeters per second. So what this does allow us to do is then plot at what speed does the river have to travel for it to move clay, silt, sand, of course, material. And obviously it doesn't need to be moving very fast to move clay because it's so small, but it needs to build up a much greater speed before it can start transporting larger particles. And that's what this curve here shows us. So it's the speed at which it can actually transport stuff. Okay, we have some other examples. World population requires the this graphing on the y-axis because whilst the x-axis is just regular intervals over time, because human beings have been on the planet for a long time, and because the world population was incredibly small if we go back thousands of years into the past, but has then grown dramatically in more recent years, in the last few hundred years, as a matter of fact, we need to use a logarithmic on the vertical scale to allow us to put the fact that the human population was a few million going back 10,000 years ago, and today stands at 8 billion. The Richter scale is also logarithmic because it doesn't go up in intervals of 1, it actually goes up in multiples. So every time you go up 1 on the Richter scale, it's actually 10 times larger than the level below. So we have to show the Richter scale on a logarithmic on the vertical axis. And here you can see some of the strengths of using it as a technique. It's quite straightforward. It allows us to plot data with a massive range with small values and large values onto the same piece of graph paper, which then allows us to analyze the gradient. But there are some limitations as outlined there, and you might want to just note down one or two in case you're asked to discuss the usefulness of logarithmic graph paper.